Good morning.
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 All right, it's 9:30. We'll get started. So we are starting on test 4 material. So just to give you an idea of the schedule here. I still recommend watching these videos as they come up, but we're going to be focusing first of all today, this being Wednesday, on drawing Lewis structures and the introduction to VSEPR. All right, so let's go ahead and get started on that. Now, the Lewis structure thing is something that we've already been working on. Let me go ahead and download the notes here. And yeah, we talked about this in module 12, but we're going to add a few wrinkles here. Let me get rid of that. To the drawing of Lewis dot structures, and we're going to introduce some exceptions to you that we're going to that you haven't seen before. Okay, so as we know about drawing Lewis structures, there are two rules that we need to follow, and those two rules are: first of all, we use exactly the number of valence electrons calculated. And if you remember, we calculate valence electrons by using the groups on the periodic table. That's the first rule. And the second rule is everything around the central atom has 8 electrons, except hydrogen, which has 2. So all the outer atoms I'm talking about. Everything around central atom has 8 electrons. H has 2 electrons. We know this. Okay. Okay. Now, there are a couple of exceptions we can make about this, and it mainly refers to the central atoms. And what we know is that if the central atom is a metal, it will not form double bonds. Oops, it's important there. I missed the most important part of that. If the central atom is a metal, it will not form double bonds. So you'll remember that when we had to get 8 electrons on the central atom in the past, we formed a double bond to make that happen. But if the central atom is a metal, it will not form a double bond. Let me read that comma there. And the other thing is any excess electrons always will go on the central atom. Sometimes resulting in more than 8 electrons. So I'm going to give you 2 examples here. And those are AlF3 and let's see, XeF4. Now the XeF4 is an interesting one because Xe is a noble gas, and you might be thinking, well, Xe being a noble gas couldn't form compounds. Well, actually, it turns out it can. Krypton, xenon, and radon can all form compounds. They're not incredibly difficult. They're not incredibly easy to make, but they can be made. But let's look at AlF3 first. And the number of valence electrons there is going to be 3 plus 3 times 7. Now we get this off the groups on the periodic table. And that would be 24. So there's 24 valence electrons on AlF3. Does anybody have any questions so far? Okay. So I don't have to go as far as showing you that on the periodic table out. So what we do is we put the F's around the atom. And then we give the F's enough electrons to give them 8. And that would mean that we've used up 24. But because this is a metal, then we don't form a double bond in order to give the aluminum 8 electrons. We just leave it the way it is. Okay, so this is different to what we had done in the past. But in the past, all we've really done here is had non-metals as a central element. In that case, we had to form a double bond. Does anybody have any questions so far? So for Xe is in group 8 and fluorine is in group 7. So that's going to be 36 electrons. And we put the Xe in the middle, we join the Fs. And then we put enough electrons around the fluorine to give it 8. And that would be a total of 32 that I've used so far. And then the other 2 pairs go on the Xe. And that would be the completed Lewis structure for XeF4. So as you can see, these are both exceptions or different kinds of ways of doing Lewis structures than what we had learned in the past. I guess you call them special cases or exceptions, but this is how we deal with them. Does anybody have any questions about either of those examples? Let's see how you're doing. Okay, 5, 4, 3, 2, 1. A couple of people don't want to vote. Okay. So does anybody have any questions? Does anybody have any questions?
So how do we get 32 for and Xe and F?
Okay, so you see here, each of these represents an electron, Michael. One,
Mhm.
2, 3, 4, 5, 6. And then the bond represents 2 electrons, that's 8. There's 4 of those, 4 8s are 32, which means then we have 4 left over that go on the XE.
Thank you.
All right. Any other questions? Any other questions?
Why does X have 12 electrons?
XE.
Oh, Xe.
Why? Because we had calculated 36 balanced electrons. Those electrons have got to go somewhere. The only place we can put those extra electrons is on the central atom. But Xe is pretty big, so you know it can handle having some excess electrons because it has access to those higher orbitals, like the 4f, for example.
Oh, okay, thank you.
That's why small atoms really can't do this. Only large atoms can carry these excess electrons. All right, any other questions? Okay. So the discussion we're going to have now is going to revolve around shapes. So doing the Lewis structure doesn't give us a great deal of information about the shape of the molecule. But shapes are always going to be determined by one premise, and that is that if you've got a central element and you've got things around it, those things are always going to be as far apart from each other as they possibly can be. So what this means is that depending upon what's around the central atom, we're going to be able to predict what the shape is, because the shape is going to be something that is always going to result from everything being as far apart from everything else as it possibly can be. Now, there's 2 things around a central element that can take up space. You've got an atom, or you can also have a non-bonding electron pair or lone pair. Those are the 2 things that take up space around an atom. And those are the things that will end up influencing what shape the atom will end up being. So we've got this list of shapes here. You get kind of like a partial list on the test. I'll show you what you get in a bit, but it's pretty much this molecular geometry column. You get that entire column on the test so that you don't have to remember the names of these different shapes. So, well, in my experience, students are notoriously bad at remembering the names of geometric shapes. So I don't force that. It's not really what I'm testing anyway, your memory of geometric shapes, but it's just something that I have noticed over the years that people don't tend to like geometry a great deal. Let me stop sharing that. So these are all different shapes for all the different numbers of lone pairs and atoms that happen to be around the central atom. So when I talk about electron groups, really an electron group is defined as being an atom or a non-bonding electron pair. That is anything that actually happens to take up space. Now, the tricky part about all this is that there's 2 kinds of shapes that we're going to talk about. We're going to talk about an overall shape, which takes into account all the electron groups, you know, the atoms and the lone pairs. And then we're also going to talk about a shape of atoms, which is what the shape looks like if we ignore the non-bonding electron pair. And when I say ignore, I mean, I'll put that in air quotes. We're not really ignoring it, we're just not showing it so much. So that's going to be what's going to drive the molecular geometry here. All right, so let's first of all take a look at some of the overall shapes that I want to discuss. And I think the best way to do this is to move this over here. Is to show you, find it here, yeah, the video. And these videos are pretty decent. This is the overall shapes video. And I'm not going to play this entire thing. I'm just going to show you some examples. The first shape that we can talk about is called linear, and you can see that shape there. It's got a central atom. It's got two things attached to it. If those two things are going to be as far apart from each other as possible, then they're going to do so to make the molecule a straight line. And that means that there's going to be 180 degrees between the atom on the left and the atom on the right, all because they want to be as far apart from each other as possible. So that's the first overall shape we're talking about. It's called linear. All right, how are you doing so far on this? Okay. So for the person who understands halfway, is there a question? Is there a question you could ask that would be appropriate here? Okay. So that's with two groups. Let's look at what happens when you've got three groups. With three groups, let me see. I'll see if I can play this a little bit so you can see me. So you can see me twist it around a bit. There you go. See. Okay, so everything's in the same plane. And this is if you've got three things attached to a central atom. And again, everything is as far apart from everything else as it possibly can be. The bond angles here are 120 degrees. The reason I know that is because if the circle is 360, and if I split a circle into three, that's 360 divided by 3, which is 120. So that's the bond angles between these bonds. You see it's a bit more than 90. 90 would be where my cursor is. But 120 would be between the two atoms. Does anybody have any questions so far? So that's 3 items. The next one is 4 items. This is called tetrahedral. And I'm going to twist it around a bit here in the diagram. So this is a tetrahedron I'm drawing on the screen now. I know you can't hear my audio, but you don't really need to. Actually, I will. I'll share the. Let me share the audio here. Whoops. Okay. You should be able to hear the audio.
For each of its 4 sides.
So this is a tetrahedron I'm drawing
There
here.
we go. So that's what a tetrahedron would look like. And if we're talking about tetrahedral shape, what you've got to imagine is that there's an atom in the center of this 4-sided figure, and that we've got atoms at each of these vertices. And the overall shape of that would be called tetrahedral. Alright, so here's an example. This is CH4. And as you can see, we've got a shape now that is no longer planar, it is 3-dimensional. Now what I'm going to do is I'm going to arrange it so these two are actually in the plane of the screen. And what you'll see is that this one's sticking out and this one's sticking into the screen.
Alright, so that's what tetrahedral looks like. And again, it's the result of having 4 things around a central object and putting those 4 things as far apart from each other as possible. I tell you, there's a lot of students who really hate geometry. I know this is killing you right now, but you know, this is just the nature of valence shell electron pair repulsion theory. All right, does anybody have any questions? Now let's look at 5. So this is what happens when we put 5 objects. Now what you'll see, it's interesting, the 5-object one. You see that there's the 2 that are pointing up and down here are linear, and the 3 that are in this plane here are actually trigonal. We looked at those earlier. That's the trigonal shape was the one that was the 3. This is the linear shape with the 2. So let's look at what happens. I'm going to show you how this looks in 3 dimensions.
And in this way, everything's as far apart from each other as it possibly can be. The name trigonal bipyramid or trigonal bipyramidal comes about because if you look at the 4 atoms here, they take on the shape of a triangular based pyramid. So there's your triangle on the bottom, and there's the tip of the pyramid right there. And it's a trigonal bipyramid because you've got a pyramid up here and a pyramid on the bottom. So that's where the name comes in.
Yeah, so that's what it's called, is trigonal bipyramidal. Yeah, so two triangular based pyramids joined at their bases, essentially.
Right, so again, we've got a linear geometry here and a trigonal geometry in the plane.
All right, so that's the result of putting 5 objects around the central atom. And I mean, that's the shape they'll take on, so they're as far apart from each other as possible. Does anybody have any questions? Okay, let's look at the 6th.
Figure. It's really like
This is called octahedral. The solid shape it represents is called an octahedron. Octa meaning there's 8 sides. It's really effectively, though, 2 square pyramids joined at their bases. It could be called square bipyramidal, I suppose, but it's not called that. It's called octahedral. You'll see that everything is pretty much linear. Everything's 90 degrees apart.
2 square-based pyramids that are interlocked at their bases, and I'm talking about this being the square and these being the tips of the pyramid.
All right, so that's octahedral there. That's what results from 6 objects being placed around the central element so that they are as far apart from each other as possible. All right, let's see where you're at with this. Okay, 5, 4, 3, 2, 1. I'm still getting some people not voting here. Okay. All right. Does anybody have any questions? So I would recommend watching that video. I think it's a pretty good one. I think I nailed it actually myself. It's up to you to decide, I guess. Okay, so that's the overall shapes. Those aren't too bad. That's when you've just got straight atoms. And if you can replace those atoms with non-bonding electron pairs, and those overall shapes would still be there. That's the tricky part that I was talking about earlier. But let's look now at the shape of atoms, which now introduces the concept of what goes on when we replace some of these atoms in the overall shape with non-bonding electron pairs. All right, so let's look at some examples of that here on the video. Let's have a look. Okay, so this would be something like SO3, and it would be a trigonal shape. That would be 3 O's connected. But what if we took one of those O atoms and replaced it with a non-bonding electron pair? Well, this would be the Lewis structure for it. And you can see that the O's would each take up space, but so would this non-bonding electron pair. It takes up space as well. The overall shape of this is still trigonal. You know, if this was an atom, it would still be called trigonal. It's still trigonal if we're talking about the overall shape. The shape of the atoms, though, is called angular, angled or bent. Angular or bent would be the name of this. And what we're in essence doing here is just saying, well, because the electron pair really is not visible, the atoms are visible, the electron pair is invisible, we still consider that it's actually taking up space and influencing the shape, but it is not really visible. So we can look at the shape of just the atoms and we can see that it would be called angular or bent. I'm going to ask how you're doing with this. I'm not expecting a great result right now, but we'll see. 5, 4, 3, 2. Okay, that's kind of what I expected. Does anybody have any questions so far? All right, well, I'll keep going with it. Hopefully you'll catch on as I go. All right, let's see. I think I might have a thing for this. There it is. So this is, let's see, I think I share this right. Okay.
Here and BF3 both have identical overall geometries. The lone pair ends up taking up just as much space as the fluorine does. So the overall shape of this, if we include the lone pair, is going to be called trigonal. However, if we decide we're going to not show the lone pair, this is what we're going to end up with. And the shape of this, not surprisingly, is called bent. The other way of naming this is called angular. Now, it's not like we've removed the lone pair. It's just that I'm not showing it in the diagram. So what I want you to see here is that there's two possible ways that we can talk about shape when lone pairs are involved. This way we can talk about the overall shape when we're actually including the lone pair in the diagram and we're including it in the overall shape of the actual structure. So this would be SO2 and the overall shape would be trigonal. When we remove the lone pair, because remember the lone pairs are invisible, we're not going to be able to see them. The only thing we're actually going to see are atoms. Then what we're looking at is just the shape of the atoms, and we call that bent. So there's two things that we'll talk about: overall shape and shape of the atoms.
Yeah, so there you go. That's another explanation and pretty much the same topic. Does anybody have any questions?
Why would that shape be bent?
Or what's it look like? Doesn't it look like a boomerang to you, Michael?
Yeah.
Yeah, that's why it's called bent. Right. It could be, maybe they should rename it boomerang. I think they should rename it boomerang.
I think so too.
Yeah, thanks, Michael. I appreciate your support.
You're welcome.
Anybody got any other questions? But I mean, is that fair enough, Michael? I mean, I think you're overthinking it if you're trying to see why it's called bent. You're overthinking things.
Yeah, thank you.
All right. Let's look at this is a tetrahedral shape. That's with all the atoms there. We looked at that earlier. Right, this is when we replace one of the atoms with a lone pair.
Atoms and one lone pair, so there are 4 objects in total around the nitrogen atom. This is still an overall tetrahedral arrangement, just like methane was. We arranged the methane in the same way, and you can see that the overall shapes are identical. If we ignore the lone pair or just don't look at the lone pair, remember the lone pair is invisible because it's just electrons. The only thing we can actually see are atoms. This is what we get. And the shape here is called trigonal pyramidal. As you can see, it's the shape of a triangular based pyramid. The triangle would be these hydrogens here, and the tip of the pyramid would be the nitrogen.
All right, does anybody have any questions about this? Okay. All right, now this one, what we're doing is we're taking the same thing and replacing 2 of the atoms now with non-bonding electron pairs.
Yeah, and methane has, and you can see them all there. We've got 4 objects around the water. We've got 2 atoms and then 2 lone pairs. And again, if we take off the lone pairs, what we're left with is a structure that is the bent or angular, just as it was for SO2.
There you go. Does anybody have any questions about that? So hopefully you're getting the idea. There's an overall shape that includes all the objects around the central atom that take up space. And then there are going to be, there's another way to describe the shape where we sort of cover up the lone pairs. We just take them off and we just look at the shape of the atoms and see what we come up with. Now remember, there's only going to ever be a difference if there's lone pairs present. If there's no lone pairs present, the overall shape and the shape of the atoms are identical. I'll say that again. If there are no lone pairs, the shape of the atoms and the overall shape are going to be the same. All right. Let's see how you're doing now. Okay. Well, I like that. That's good. Okay. So nobody has any questions, I'm guessing, or does anybody have any questions? So we can continue this reasoning and this thought process, of course, for a bunch of other things as well. Let me enlarge that a little bit. Okay. So we can do, that's the trigonal bipyramidal shape that's got 5 objects around it we talked about earlier. If you replace one of those with an electron here, the shape we end up with for the atoms is called a seesaw. If we take two of the atoms and replace them with lone pairs, we get T-shaped. And then if we replace all 3 lone pairs, then we get linear. So those are all overall shaped trigonal bipyramidal because there's 5 objects. But because we've replaced some of those atoms with lone pairs, we get different shapes of the atoms. Does anybody have any questions? Okay. You won't have to remember any of this. I give you these shapes and these names on the test. Okay. The last one there, octahedral, you can see it's got 6 objects around it. If we replace one of them, we'll get the shape square pyramidal for the atoms. And if we replace 2 of them, we get square planar for the atoms. So those are all the examples we're going to be talking about. They're the only ones we're really going to consider. All right, so that's my introduction to overall shapes and to shapes of atoms. All right, now we're going to move on to something that's a little bit more difficult, and it has to do with dipoles. And this one is a bit harder to deal with. Okay, so dipoles. Let's look at what a dipole is first. Let me okay, let's have a look. Okay, dipoles. We haven't done orbitals yet. I'll get to that in a minute. Well, actually, I guess we'll do orbitals now. Okay. Orbitals. Now, orbitals aren't too bad. We talk about orbitals in the context of, let's see, here we go, S and P. So we'll just look at S and P's first. And if you remember what S and P orbitals look like, they look like what you're seeing here. The S orbital is round or sort of spherical. The P orbitals are dumbbell shaped, one along each of the axes X, Y, and Z. And if you were to look at a C and you would say that it was tetrahedral. So here we're already saying we know the shape, right? So C, and we know it's tetrahedral. And that means it's got four groups attached. And those groups can be lone pairs or atoms, it doesn't really matter. Now, if we look at the electron configuration, for carbon, it's 1s2, 2s2, 2p2. It's 2 plus 2 is 6. Okay. So when you look at carbon, initially you see these two lone pairs of electrons here, and you might be thinking, well, that means that carbon can only bond once. But if we know it has 4 groups, then we know that that's not possible. It must have 4 unpaired electrons that are capable of bonding. To explain that, what we do is we invoke a concept known as hybridization. So that the 1s electrons aren't involved in bonding, they're not valence. But what we can do is we can take these 4 orbitals, 1s and 3 p's, and we combine them together to form what we call hybrids. And these are called hybrid orbitals. These are sp3 hybrids. So this is what I've done here. So this is carbon that I have on the left side, and on the right side I've got the hybridization there. So each of those hybrids is 1 part S, 3 parts P. Effectively what I've done is imagine that you've got liquids here of different colors. I know you can't see the colors here on this diagram, but it turns out that one is, let me think, blue. That one's blue, and these guys up here are yellow. And when you add blue and yellow together, you get green. And so if you take all of those orbitals, you mix them up into the same pot, you'll get this green mixture. Now, the other way of looking at it is to make that vodka and make these orange juice, right? So make the bottom one vodka, this one orange juice. Does anybody know what this would be called if we mixed all that together? Vodka and orange juice, come on. Somebody's got to know. You're telling me nobody knows.
Screwdriver?
A screwdriver, thank you very much. It's a screwdriver. Now you all know what I think you all know what a screwdriver looks like. It's kind of the color of orange juice really, isn't it? But a little bit lighter perhaps because the vodka is colorless, right? So that's 1 part vodka, 3 parts orange juice. 1 part S, 3 parts P. That's what I mean by that. So when you take that and you put it back into those glasses, then you've got one, with everything here is still 1 part vodka, 3 parts orange juice. But they're all going to be the same. And that's what's going to result in the tetrahedral shape, because those 4 electrons then can be placed 1 in each of those hybrid orbitals. The word hybrid itself means a combination. It's like if you had a lion and a tiger. Does anybody know what the hybrid's called when they have a cub? Anybody know? It's called a hybrid.
A liger?
A liger, that's correct. Yes. So a lion and a tiger make a liger. So that's, if you didn't know that, you learned something today. You might have even seen one, and you never had one at Busch Gardens, I think. Does anybody have any questions? If you haven't seen one before, look it up. It's a true thing. I didn't make it up. All right, so that's what hybridization looks like. Now, the point is that the number of hybrids we get is going to be the result of knowing how many electron groups we have around the central atom. So this is always going to be based on the overall shape. Just to give you an idea what the hybrids look like, you can see that the sp3 hybrids, not surprisingly, look more like p orbitals than they do s orbitals. Now, I've got them up here. The p orbitals you see are dumbbell shaped. The sp3s are kind of a little bit fatter in the top than they are in the bottom. So that's kind of the s influence there, but it's still 75% P, 25% S. Now in the sp2 hybrid, that would be for 3 groups. You can see the sp2s are a little bit shorter and fatter. That's because now there's more S influence. It's 33% S, 66% P. And then if you look at the SP, which would create a linear situation, then what that does is that gives you really fat orbitals that look kind of half like S, half like P, 50% S, 50% P, to provide us with this kind of thing. I'm not even going to do the polling right now because I know that some people have no idea what I'm talking about, but that's okay for right now. The main thing is let's talk about the sp3 hybrids here. Let me see how you feel about just the sp3 hybrids. I think this is just somebody answering my screwdriver question. Oh, for legal reasons, no. Okay, fair enough. Doesn't mean you can't know. Good golly. All right. Let me see. What am I doing? That's right. Yes, let's poll. How you feel about sp3 hybrids? Let's see. How do you feel about sp3 hybrids? Five, 4, 3, 2, 1. Okay. Does anybody have any questions to help out here? Okay. So let's look at the summary I've got over here. So this is, again, all going to be based on the overall shape. So once you know the overall shape, then you pretty much know what the hybridization is going to be. So for linear, there are two groups attached to a central atom. So what I'm talking about here, this is linear. Two groups, that means we need two hybrids. So the hybridization would just be sp, so it'd be the combination of one s and one p, and we'd have two of those sp hybrids. Trigonal, we have 3 total groups, we need 3 hybrids, which would indicate that it would be sp2, that's 1s and then 2 p's to give 3 total, 3 orbitals needed to make up these 3 sp2 hybrids. Tetrahedral, we just talked about 4 groups, 4 hybrids, sp3. Now, trigonal bipyramidal 5 is going to be sp3d. Now, remember, we run out of p orbitals, so it has to grab a d orbital from the next level. So it's going to be sp3d, and octahedral is going to be sp3d2. So the overall shape will always dictate to hybridization. So you can see you're always going to have as many orbitals in the hybrid as we have total groups. I'll say that again. There's as many orbitals in the hybrid as there are total groups. Well, how do you feel about that statement? I'll say it again. There are as many orbitals in the hybrid as there are overall groups. How do you feel about that statement? Five, 4, 3, 2, 1. All right, good. There you go. So everybody understands that. That's nice. Okay. We're going to move on now to dipoles and net dipoles. Now, the dipoles thing is kind of difficult. We have dealt with this before, at least the dipole part. We dealt with it when we were talking about polar covalent bonds and polarity of atoms. And when we're looking at this, I've got 2 examples here. We have 2 elements joined to each other or bonded to each other, and one is more electronegative than the other. Now, in this case, F is more electronegative than H. So what happens is that we can put these partial charges on these elements. I feel drawn now to pull up a periodic table. And I'm just trying to see if I have one here. Hang on. See if my lecture section is good. Do I have one? Not in this folder. Let's go back to test 1. I have one there. Okay, I'm going to pull up this periodic table here. All right. So we know from the periodic table that fluorine is the most electronegative element. So whatever's closest to fluorine is always going to be more electronegative. Now, electronegative means that it attracts electrons towards itself, which means that when we're looking at something like this, what we're saying is that there's a more of a partial charge on the electronegative atom than the one that is less electronegative. The other way of looking at it, and I'll just show you this in an HF bond situation, is that because F is more electronegative than H, what it means is the electrons on average are closer to the F than they are to the H. Does anybody have any questions? All right, how do we feel about the partial charges? This is not something you should have seen. You've seen this before, but we'll see. How do you feel about the partial charges? The delta plus and the delta minus. See where we're at. 5, 4, 3, 2, 1. Okay, anybody any questions about the partial charges?
So why is F more electro charged than H?
Well, I don't know. It's like asking why the sky is blue, Michael. It just is. Well, I know there's an explanation to it that has a Rayleigh scattering, but I'm just saying that I want you to accept that fluorine is the most electronegative element.
Okay.
I mean, I can go into a greater explanation of it, but it has to do with the nuclear charge and the proximity of electrons to the nucleus, and the fact that F has everything. It's kind of like the last element in that row, and it's got the highest nuclear charge, the highest number of protons, and then it would like more electrons in order to get to its octet as well. So those are all factors that lead F into being the most electronegative element. But this is something we dealt with before back in intro chemistry, and the beginning of this course as well.
Thank you.
All right, does anybody have any other questions? Okay. So you can see that it depends on which element is more electronegative. O is more electronegative than H. So O gets the delta minus and the H gets the delta plus. Now, what we can do then, once we know which one has a delta plus and delta minus, we can draw another representation. This is called a dipole. This dipole is effectively what's known as a vector. Now, if anybody's ever done any calculus, you'll know exactly what I'm talking about. If you've never done calculus, vectors might be very foreign to you. Where do you learn about vectors? What course? I know some of you have done higher math. No, nobody's ever heard of vectors before? I can't remember.
Heard of that
I do
before.
vectors in physics.
Oh, yeah, well, yeah, you just dealt with in physics, but maybe none of you have taken calculus, perhaps, I don't know. But anyways, yeah, it is dealt with in physics too, physics as well, I should say. But there's a lot of math in physics, hey. All right, so these are the way that these are drawn is that you can see that at this end it's a little plus, so it's drawn from that, and then the arrow is drawn towards the more electronegative element. So it's like it's showing you which way the electrons are being drawn to, and this creates what we're calling a dipole, and it's the result of the electrons being closer to one element than the other. That's all it really is. And it always points in the direction of the more electronegative element. Does anybody have any questions? Okay. So when we're dealing with dipoles, what we talk about is something called a net dipole. And the net dipole is going to be the sum of those vectors or the sum of those dipoles. And yeah, this is not a really easy concept to explain, but I'm going to do my best. I'm going to use a video. A video to explain these. Okay. This is a really good video, by the way. I would really recommend watching it.
I'd like to
So I go through the explanation of what dipole is to begin with, and where we get it from, and delta pluses, delta minuses. And then I do some examples of how we can calculate dipoles. Now remember, dipoles are only going to be along bonds. We never put dipoles along non-bonding electron pairs because they're not bonds, right? They're just electrons. So I'm going to show you how we show the dipoles on these different examples. This is a good introduction. Let me take it back to the beginning of that. All right.
All right, so that's for just one single bond. What we are going to look at now is what happens when we combine dipoles, and we look at net dipoles. That's for compounds with more than one dipole in their system. I want you to consider some examples here, and I've just pulled these examples out of the ones that we looked at earlier. Let's take a look first of all at SO2. If I drew a dipole, the first thing I would want to do is draw dipoles along the bonds, and I would first of all also want to see which out of O and S was more electronegative. So what I do is I go to the periodic chart, I see that S and O will be more electronegative than S will be because O is closer to F. And that means I can draw two dipoles along here, and the dipoles will be drawn from the S towards the O in both instances. Now the dipoles will also have the same magnitude because I'm drawing them to the same atom. Now the other thing I'm going to do is I'm going to look at this and try and tell which direction the net dipole will be going in. Now the net dipole,
When I use the word magnitude, it just means size. So they're the same length. The vectors and the dipoles are the same length because they're going to the same atom. That's what I meant.
will be a combination of these two dipoles. Now we can do this by using the concepts of vector addition, which I'm not going to be looking too much at, but I do want to just be able to describe this to you. What I'm going to do is I'm going to try and draw these. That's what I was trying to do just now. Just draw this particular one and then draw this one. And what I'm doing is I'm doing vector addition, which means I'm adding these two vectors head to tail. So I'm taking the tail of this one and putting it on the head of this one. Now the net dipole then will go from the tail of the first to the head of the second. So that's going to be the net dipole, and that's going to look like, it's going to look more like this, sort of straight down through the center of the molecule. Alright, so that's what we're going to see. If we try and add these dipoles together, we're going to get one dipole, which is a net dipole, and this is the only dipole we're going to see for the entire compound because it's the combination of these two. Now, you don't have to go ahead and do this whole vector addition thing. What you can do is you can just look at the molecule and look at the direction you think the dipoles are going to add up to. So if you've got a dipole pushing down in this direction and a dipole pushing down in this direction, the net dipole is going to lie directly in between them and go straight down in the same general direction as both of these arrows.
Right. Does anybody have any questions about that? Because that's really the best way of representing a net dipole, just a combination of the two dipoles. I'll see how people feel about it. I know how do people feel about my explanation for the net dipole that's resulting from SO2. How do you feel about it? 5, 4, 3, 2, 1. Okay, that's good. I mean, that kind of surprises me. I kind of thought more people would have issues with it. Does anybody have any questions? Okay.
I'm going to try and do that over here on this particular one as well. Let me change colors. And what I'm going to try and do is draw the dipoles on this diagram here. And again, we're saying that this is an S and this is an O, so that dipole will be there. And this dipole will be here. So that's the individual dipoles for the bonds. Now let's look at the net dipole, and the net dipole is going to go straight down here and in between these two oxygens. Now the lone pair of electrons here is not a bond, so I do not draw a dipole along a lone pair of electrons. There needs to be something at the other end if we're going to have a dipole, and there's nothing at the end of an electron pair. So we are only interested in dipoles along bonds, and that's it. So that's where the dipole would be for that. Well, let's take a look at water. Now with water, oxygen is more electronegative than hydrogen. So when I draw the dipole, I draw them directly parallel to the bonds with the arrows pointing towards the oxygen and the plus on the hydrogen end here. I'm going to draw those on the 3D model as well, remembering that the lone pairs, that's the pink ones here, do not get dipoles. Alright, so I'm drawing the dipoles along the bonds pointing towards the more electronegative element. Now what's going to happen is I'm going to be able to draw a net dipole, and the net dipole is going to be pointing upwards and straight through the center of the molecule. So that's going to be the combination of these two here. Alright, let's take a look at Na.
All right. How do you feel about water? Five, 4, 3, 2, 1. All right. Anybody got any questions they can ask? It's 11 to 4. Anybody got any questions? All right.
H3, we'll do the same thing. Again, nitrogen is more electronegative than hydrogen, so each of those dipoles will point in towards the N. This one's a little bit harder to draw because it's kind of behind. Now what we're looking at here is all of these dipoles pointing in and up towards the nitrogen. The net dipole is going to run through the center of the molecule and point upwards in the same general direction as these dipoles here are pointing. Again, notice that we do not put a dipole on the lone pair of electrons. I could have.
All right. Okay. How do you feel about NH3? How do you feel about NH3, the one we just did? 5, 4, 3, 2, 1. Yeah, I keep on losing people. I don't know. All right. Does anybody have any questions? Does anybody have any questions? I think it's worth watching that video. I mean, I think it's a good one. I think it really does explain the concept of those dipoles pretty well. So, but you know, if somebody has any questions now, obviously there's people who do still have trouble with this. So, if you have any questions, now's the time to happen. Any questions? All right. Let's take a look at an example of, well, I'll take a look at some examples of these on the test. I think it's probably the easiest thing to do right now. I think one of the best ways to practice this concept, obviously, is to do this test. Now, here's what I give you. I give you all of the shapes and their geometries, and these are all really shapes of atoms. But all of these do have the same overall shape, and they have the same number of atoms around the central atom. So when you've got 4 atoms around the central atom, it's tetrahedral. The trigonal pyramidal has an overall shape of tetrahedral, and the angular has an overall shape of tetrahedral. So you see they're all grouped together as well. So these are all the trigonal bipyramidal overall shapes, these 4 here that I'm showing with the cursor. And these 3 are the ones that are all octahedral overall shapes. Okay, so these are all shapes of atoms that you're seeing here. Okay, so let's see how we do something like this. So we've got to draw the Lewis structure of SO2, how many double bonds are present. This is something we already did back in test 1 or 2, back in test 2, I think. And figuring out how many lone pairs are present. All right, let's see how we go with this. So valence electrons here would be 6 plus 6 times 2. Now this is from the groups, they're both in group 6, which is going to be 18. So we go ahead. Now S, remember, is a non-metal. And we join the O's, and then we give the O's each 6 electrons to make up the 8. That leaves 2 that we put on the central element. That gives us a total of 18. The sulfur, unfortunately, only has 6 electrons, 1, 2 for the lone pair, and then 2 each for the bonds. That's a total of 6. So in this instance, we need to use electrons from the O. I know I'm going through this fairly fast. It's because we've done this before. And that gives us what the Lewis structure would be for SO2. We form a double bond by taking 2 electrons off the O and putting them into the SO bond. And the reason we had to do that is because we'd already used up all 18 electrons. We didn't have a choice. We can't put just an extra 2 electrons on the sulfur, just pull them out of the air. They've got to come from somewhere. And we do that by creating a double bond. Yeah, so the answer there would be 1 double bond. Does anybody have any questions? How do you all feel about that one? See how good your memory is. Five, 4, 3, 2, 1. Okay, looks like everybody understands that. That's good. All right, so F2O, valence electrons are going to be 2 times 7 plus 6, 20. So put the O, put the F's connected to it. I put enough electrons around the fluorines to give them 8. That means I've used 16 so far. That's 18 and that's 20. So everything's satisfied. There's no need for any double bonds. This would have a total of 8 non-bonding electron pairs or 8 lone pairs. All right. Anybody got any questions? Okay. All right. Let's talk about this one here, CH3 minus. Now this reintroduces a concept we had talked about back when we did Lewis structures, and that means just calculating the, oops, try that again. That means calculating the valence electrons for something that has a charge on it. And that would be CH3 minus, which would be 4 plus 3 for the hydrogens, and then plus 1 for the negative charge, right? So we always add 1 for each negative charge. We subtract 1 for each positive charge. That would be a total of 8 valence electrons. So the way it would look is we would do the hydrogens for carbon. That's 6. To put the other 2 on the central atom, that's a total of 8. And that's what the Lewis structure would look like. So when we look at it, we need to figure out, we're looking for the overall shape, which includes the lone pairs. And you'll see there's 1, 2, 3, 4 total groups. And the thing that has 4 total groups on it, I just like to look at the one that's got all the atoms, just sort of pretend the lone pair is an atom to get the overall. And the overall would be tetrahedral. So that would be the answer there. All right, let's see how you feel about that one. All right, how do you feel about the overall shape being tetrahedral? 5, 4, 3, 2, 1. Okay, everybody seems to understand that. Let's look at the shape of the atoms for Ni3 2 minus. And that would be 5 plus 3 times 7 plus 2. That's 28, I believe. So N, we've got 3 I's. And we would put our electrons around first. Okay, that's a total of 24 so far. And then, oops. And then we have 4 left over. Those all have to go on the central atom. So we've got actually here 2 lone pairs on the central atom and then 3 atoms. That's a total of 5. So the shape of this overall would be trigonal bipyramidal, but the shape of the atoms, we have to go find the one in the diagram that looks like this, that has the 3 atoms and the 2 lone pairs on it. Let's put parentheses here too. And you'll see that that would be this one, which is called T-shaped. Right, so that's T-shaped. That would be the one that is we choose for that as the shape of atoms. All right, how do you feel about that one? Five, 4, 3, 2, 1. Good. Any questions? Okay, I'm going to leave it there for today. I need to go do something, but I will see you all on Monday. We'll continue with the examples from the test.
See you Monday. Have a
All right,
nice day,
thank
Professor.
you. Bye. Bye.
Thank you, Professor.
Professor, I have a quick question.